So let's look at it in an example. We need to apply the conservation of mechanical energy, or we call it version 3, and when there's no non-conservative force doing work. Okay, so in this drawing it shows a person starting from rest at the top of a cliff, swinging down, and at the end of the rope, release it and falls into the water. So there's two different ways to do that. If the person release the rope at this position, and then he's going to fall into the water along the path 1 and enter the water at this point. And then it's going to have a velocity, we call it v1 equals 30 meters per second. But if the person continue to follow the path 2 and then release the rope at the point 2, and then he's going to have this velocity v2. And this is the location 5.2 meter above the water level. So the question asking for what would the velocity be of this v2 if he's going to release the rope at this position. So basically we look at it in this case. So these two positions during this motion, there's two forces acting on the person. One is the tension force, and one is the gravitational force. But the tension force is always perpendicular to the direction of displacement. So the tension force is not doing work. And then there's only one force, the gravity, is doing work. And since the gravity is a conservative force, that means the work done by the non-conservative force equals 0. And then basically we have this simplified version of work energy theorem. We also call it version 3. It means delta KE plus delta GPE equals 0. Or we can write it as this format. It means KE initial. Now here we didn't use initial final, we just use 1, 2 because it represents the two positions. So position 1, position 2, so each one we use KE and the GPE and represent the total mechanical energy. So total mechanical energy is conserved, so they're equal. And then since we're talking about the gravitational potential energy, we need to set a reference of this GPE equals 0 at the position 1, which is the lower position of this 2. And also and then we should have this GPE1 equals 0, right? And we also know the initial velocity here, so we plug in everything, replace all the KE1, KE2, and GPE2 with their corresponding formula. So 1/2 mv1 squared equals 1/2 mv2 squared plus mgh2. So the h2 is the height of the position 2 above the reference. And then you can see we cancel the m, and then we multiply 2 on both sides of the equation. So we got v1 squared plus equals v2 squared plus 2gh2. And then just isolate the v2, take a square root, and you can see this is actually looks very familiar to the kinematics equation. Okay, and in fact that's true. And then we just plugging everything. I forgot to put an h2 here. It's supposed to be h2, which is 5.2 meter. And plugging and calculate, we got 8.2 meter per second.